Right. It's nice to see some of your faces when I'm talking, so I feel like I'm actually talking to a class instead of some blank means. All right. Okay, so I believe what I had mentioned last time is I would go over um, sample questions in chapter 6. So I've created this handout, which I will post after the session. Um, and a second here, let me actually share this with you. All right, so in the beginning of this handout, there's 7 pages to it. There's some introductory definitions, like what a probability experiment is, sample space, event, what probability is. The probability goes from 0 to 1. And then the idea that we could, use these capital letters to equal an event. Use any of our capital letters for that. We know the probability, and the way we denote the probability of an event is with P, within parentheses, with the event inside the parentheses. Okay? We also talked about the complement of an event, which is everything else in the sample space other than that event. So therefore, the probability of the event plus its complement. Now, notice here I used apostrophe, but that's one of the choices. You can also use C. So if you see apostrophe, you see a C, it means complement. So I'm showing you this notation also, so that if you see it, you know it means complement, along with the superscript C. All right, and we know that the sum of the probability of an event plus its complement must always equal to 1. It's absolutely certain that if you find the probability of A and you find the probability of its complement, we find the probability of the entire sample space. All right. Also defined the 3 probability approaches: the classical approach, which is the one where we're flipping a coin or rolling a die or playing cards and maybe playing poker, where we can determine the probability of an event before we actually play the game. All right, we can determine that probability. So how do we do that? We just count the number of outcomes for the event, and that's our numerator, and we divide by the number of possible outcomes in the entire sample space. Okay. Relative frequency approach is a little different, where we're actually going to run an experiment over and over again. For each time we run it, it's called a trial. So the number of trials in which we see the event A is our numerator, and the total number of trials is our denominator. Of course, when we do surveys, this is the approach that we're going to be using, where the total number of trials will be the total number of people in the survey. Subjective approach just means that. It just means somebody's belief in what the probability could be based on their experience or just a guess. I also brought in these things here, which you can look at if you like. I'm not going to test you on odds. It's not in your textbook, but frequently in in sports, if you ever hear somebody saying the odds of somebody winning the Super Bowl, they're referring to this type of calculation. So what is the odds of event A occurring versus event B? Suppose there's 2 events. Let's say it's 2 teams playing for the Super Bowl. All right, so event A is one team winning and the event B is the other team winning. The odds in favor of event A occurring versus event B would be the probability of A in the numerator divided by the probability of B. Typically, we don't, when we make this division, we typically will say something, the odds are 2 to 1 or 1 to 2, something like that. Odds against of event happening is just the inverse of that. And by the way, in sports, when they talk about the odds of winning the Super Bowl or winning the World Series or whatever it might be, it's odds against that they're using, not odds in favor. And they do it for psychological reasons. I'm not going to get into that because we don't really cover this in our course, but just so that you know what odds really mean. Now, some people, when they use the word odds, they really mean probability. But again, People who are in the gambling business, they know what odds means. They know exactly what it means. They know it's these calculations here. And they hire, obviously, they hire mathematicians and statisticians to for their business. All right, forget about that for a minute. Let's go back to some of the rules of probability. We know the probability has to be between 0 and 1, any probability. And sometimes we can combine events together in different ways. We discovered one of those earlier when we talked about the complement of an event. The complement of an event is all the outcomes in a sample space other than the outcomes in event A. Sometimes we can combine two events together in different ways. One way is called A or B. All right, A or B. We use this sort of U-shaped symbol here. And notice here, the general form of it is this one down here, A union B, which means A or B probability. Now, what does that mean, A or B? It means the probability of A occurring, or the probability of B occurring, or the probability of them both occurring. So the general form is that we add their individual probabilities, and then we subtract A intersect B, or A and B. And that's because probability of A and the probability of B both include the possibility of A and B occurring together. So we're double counting when we add these two probabilities together. To get rid of the double counting, we subtract one of them. If they are mutually exclusive, however, there's no such thing as A and B, because that's what mutually exclusive means, that it's impossible to have A and B occurring at the same time. So there's no way that you can have A and B at the same time. So this is 0. Probability of A intersect B is 0, and we end up with this special case here when we simply add up the probabilities. So the probability of A or B when A and B are mutually exclusive is simply the sum of their probabilities. In addition, we have what's called the multiplication rule, which we went over last time. The general form is this one right here. Okay, this is derived, by the way, from what? Derived from the definition of a conditional probability. These probabilities here. I'll get to that in a second. But anyway, the general form is that the probability of A and B is the probability of A given the knowledge of B times the probability of B, or if the problem has the reverse probability, that is the probability of B given the knowledge of A, we multiply that by the probability of A. One of these two is going to be the one that we're going to look at when we do the multiplication rule, depending on what's given in the problem. But both of those, the product of both of these is equal to the probability of A and B. Then the conditional probabilities, these are the probabilities where we have some knowledge of an event. We want to see if that changes the probability of another event. So the way to read this is the probability of A given knowledge of B occurring. And it's the ratio of these two probabilities, probability of A and B divided by the probability of B. Now, notice that the denominator's probability is based on the event that we know has occurred. That's, in this case, B. If we reverse the probability of B given that we know event A has occurred, then the numerator is the same, but notice the denominator now is probability of A. All right, so we always put the probability of the event that we are aware of in the denominator for these conditional probabilities. Now, the probability of A and the probability of B are called marginal probabilities. They are probabilities that are not based on any other event occurring. Okay. And then we can call these probabilities, the probability of A and B, we call them joint probabilities, because the word joint means together, right? So A and B together. All right, now, in your book, there's going to be certain problems. I'm going to not spend a great deal of time on each of these problems because I'm going to ask you to actually do some of these in homework, all right? Now, I may change what I'm asking as a question as opposed to what's in the book, but if in section 6.1, basically, it's all about listing outcomes, all right? And let me just give you a brief idea of what these problems are asking for. So this is both obviously in your textbook and also in the ebook at the end of section 1 in chapter 6. And this is problem number 5. So problem number 5 is basically, it talks about a tennis shop selling different brands of tennis rackets. All right. And they come in different sizes. There's a mid-size and an oversize. All right. So those are 2 sizes of the rackets. And then they have 5 different brands: the Head, Prince, Slazenger, Wimbledon, and Wilson. All right. They're listed in the book. So, so again, the first 2, so what I did here was I created events here, basically using letters that represent the event. All right, so M for midsize, O for oversize, kind of makes sense to do that. H for head, that's brand. P for Prince. Yeah, there's 2 W's here, Wimbledon and Wilson, so I decided to say W with a small m is Wimbledon. I'm using 2 letters instead of 1 here to represent Wimbledon. W with a small s to represent Wilson, and the big S to represent this brand called Slazenger or Slazenger. I don't know how to pronounce that. All right. Anyway, in the book, they give you 3 events. They describe the 3 additional events: A, B, A and B. And what A is basically is the event that an oversized racket is purchased. That's all they're telling you. And they want you to list all the possible outcomes. Well, O is the oversized, but I'm putting in comma here the other variable that's listed here, which is the size of the racket. So the racket's either going to be oversized or, I'm sorry, not the size of it. The other variable is the brand of the racket. So the event A is that all the rackets are oversized. So they're all going to have O in them. And each one of these pairs here is basically the size of the racket and the brand. So O, comma H is an oversized head racket. O, comma P is oversized Prince racket. So obviously, if A is just the oversized rackets, how many outcomes are possible? 1, 2, 3, 4, 5 for the 5 different brands, right? On the oversized racket, there's only 5 outcomes possible. B denotes the event that the name of the brand purchases begin with a W. Well, there's 2 that begin with a W, the Wimbledon and the Wilson. Okay, so what are you going to do? You're going to list all the Wimbledon ones, which is going to be the mid-size and the oversized Wimbledons, and then the mid-size and the oversized Wilsons, and that's what is listed. There are only 4 of those. And then C is asking, what is the event of not, remember the C here or an apostrophe indicates the complement of event B, which means not B. So you want to find all the possible rackets, oversized and all the brand rackets that are not B. So you want to list all the others other than what's in B, but what is listed in B here, all the other possible ones. All right. So the mid-sized ones for Head and Prince and Slazenger would be not in B, and then the oversized ones in the same for the same brands also would not be in B. All right, get the idea? So this is a good way if you're not sure of what the outcomes of an event are, is just to list them, and typically you list them in brackets. In this case here, I'm using parentheses with a comma, and I'm putting the 2 variables in that inside those parentheses. That's because I'm trying to list all the possible outcomes. So there's outcomes that have to do with size, and there's outcomes that have to do with the brand of rackets. So this is a good exercise in thinking about outcomes, all right, and listing them. The same thing for 6, 7. This has to do with computers, I believe, and laptop computers. And apparently there's a new brand of laptop computer. You can order them with 3 sizes and 4 types of hard drives, sized hard drives. So they don't, list them as S1, S2, and S3 in the problem if you read the problem, but these are what I'm listing them as, because S is representing screen size, and I'm saying S1 is the 10-inch one, S2 is 12-inch, S3 is 15-inch. So this is my own way of doing it, and you can have your own way, but this seemed like a clean way of doing it. And for the hard drives, I use H for hard drive, and H1 is the smallest hard drive, H2 is the next smallest, like that, up to H4. Those are 4 hard drive sizes or capacities. Then it says, go ahead and create a tree diagram. And they describe what a tree diagram is in 6. So what you do is you take one of the variables and you start off with this little point here called a node. And then you just branch out for all the possible hard drives. In this case, there's H1, H2, H3, and H4. And each of these hard drives will have 3 types of screen sizes, S1, S2, and S3. So the whole idea here is when you get out to the furthest branch, you're going to have combinations of hard drive and screen sizes. And how many are there? There's 1, 2, 3, 6, 9. There's 12 different combinations, right? For example, if you go along this branch, H1 and then S1, you're going to have H1 and S2, H1, S3, like that. Same thing with H2, H3, and H4. So there are 12 different outcomes in this experiment. All right? And that makes sense. 3 times 4 is 12. You multiply. How many different possible outcomes are there? There's 12. But the tree diagram is for people who like to visually see those outcomes branched out like this. This is a convenient way of doing it. And then they define outcomes A and B in the problem. A is the event that the order is for a laptop with a screen size of 12 inches or smaller. Event A, screen size 10 inches or smaller, and event B is hard drive 100 gigabytes, or it says at most 100 gigabytes, at most. Now, by the way, if they say 12 inches or smaller, or at most 100 gigabytes, it means the same thing, doesn't it? At most and less than or equal to mean the same exact thing. All right. Now, the first part here in this problem here is they're saying what is the complement of A. All right. So you have to figure out what A is. A are all the computers that have screen sizes 10 or 12 inches. Okay. And there's obviously 15-inch screens. So the complement would be all the laptop computers that have screen sizes of 15 inches, which is S3, right? So it would be H1 S3, H2 S3, H3 S3, H4 S3 would be those 4 that are listed. You can see them I listed in here. Then A union B, A or B. Well, A is screen sizes of 10 inches or 12 inches. B is hard drives of 50 gigs or 100 gigs. So what does A or B mean? It means everything that's in A or B or in both. Now, the best way of doing this is list everything in A first, which is what I did here, which is all the ones that have screen sizes of 10 inches or 12 inches. All right, so I listed them all first, all right, which is all of these up to H4S2. And then B, they say, or B, then I listed all the ones that were in B that were not already listed before in A. And what were they? They were H1S3, H2S3. In other words, they're the so B included the gigabytes that were 50 or 100, right? 50 or 100, that's H1 and H2, but we needed to include also screen sizes of 15 inches. All right, so that's how I did it. I just listed all the ones for A first, and then I found the ones in B that were not already listed, and they were these 2 here. And then A and B means all the ones that are in common between A and B. All right. So we have to look at A, we have to look at B, and see the ones that are the same. Well, B is 50 or 100 gigabytes. A is 50 or 100 gigabytes hard drive. A is 10 inches or 12 inches. So let's just go here. And which ones are in common between those 2? Well, the screen sizes A and are 10 inches or 12 inches are S1 and S2, and the hard drives are 50 and 100, which is what? H1 and H2. So obviously, it would be those four. It would be H1, S1, H1, S2, H2, S1, H2, H2, S2. They're the ones that would be in both events. And then 1614 and 1615 are giving you some practice using Venn diagrams. This is another way of displaying these events. Venn diagrams are used in sets. You might have learned about Venn diagrams when you were in high school. And what you do is the box, that rectangular box represents the sample space, everything. All right, that has to do with this problem. In this particular case here, it's problems 14 and 15 in chapter 6, or excuse me, section 1 of chapter 6. And these have to do with plants at different sites that were completed by the contract date. So these are the events that, and I'm listing them exactly the way they're listed in the book, in the problem. And then what they're asking for is they want you to create a Venn diagram for each of the different situations. For example, A says at least one plan is completed by the contract date. At least one event is completed by the contract date. What does that mean, at least one? It means either the first one, either E1 or E2 or E3, or maybe E1 and E2 only, or E2 and E3 only, or all three of them. In other words, everything inside these three circles. Now notice I intersect all three circles together, because that's the way they did it in the book. So this is really the union of these three. When we say at least one plant, we're really talking about the union of these events. The next one asks for all plants are completed by the contract date. Well, that would be E1 and E2 and E3. We use intersect. And where do all three of these circles intersect? Right in the middle. That's where the intersection of all three events occur. And that's what we're looking at. It's the event that's shaded in the middle. The other C is asking for none of the plants are completed by the contract date. Well, if all the plants are completed is the shaded circles, then if none of them were completed, it would have to be everything outside those three circles. All right, everything outside the three circles that's inside the box. And 15 is just asking some additional questions. It's saying only the plant at site 1 is completed by the contract date. Notice it says only the plant at site 1. That would be shaded the E1 here, but not where it intersects with E2 and E3. Because it's only E1 that's being done here. And notice the way I did the sets here. It's a little complicated to understand. I'm not going to ask you to ever do this here, but what it's saying is it's E1 and the complement of E2 or E3. Now, what is the complement of E2 or E3? E2 or E3 is these two circles with E2 or E3. And if it's not that, it would be the E1 only plus everything outside these three circles. But E1 and that would only be the E1 only here. So this is, again, don't worry if you don't understand that. E1 only means this area here. All right, that's what it means by it. And a lot of students, I'm telling you, when they look at problems like this, when they say E1 only, they think it's the entire E1 circle. They always make that mistake. If I say only the first site is completed by the contract date, it means it can't be E2 or E3. That means the intersection of E1 and E2 and intersection of E1 and E3 cannot be colored in. It just cannot be. Right? And then the B is asking exactly one of the three plants is completed by the contract date. Well, that would be You know, we did one of them with E1 previously, this one here in A, but if it says exactly one, that means either E1 or E2. So either E1 only, or E2 only, or E3 only. Notice where they intersect, none of that is colored in. And then the last one's a little tricky, but not too bad. It says either the plant at site 1 or both of the other 2 plants are completed by the contract. Well, either the plant at site 1. Now, when they say either the plant at site 1, they're not saying at either the plant at site 1 only. It just said either the plant at site 1, which includes this whole circle E1. And then they said, or both of the other 2 plants are completed by the contract date. All right? Both of them, which means the intersection of E2 and E3. The intersection of E2 and E3. All right. So when we say either plant site, either E1 or both of the others are completed by, we have to include this little piece right here because both E2 and E3 together would encompass this entire area here, if you can picture that. All right. E2 and E3 is just the entire intersection of E2 and E3. All right. So that's section 1, and it's basically how do we list events. And here in the last part of section 1, we were combining events together and how to show them with a Venn diagram. Now, section 2 did not have any problems, but section 3 does. Section 3 is just some basic probabilities. And section 3, number 19, has if you look at, I don't know if you have it in front of you, but basically it's a chart that has the number of songs downloaded, goes from 1 to 5 and then 6 or more, and then it gives the estimated probability of each of those those events of the number of songs downloaded. All right. So the first question says, what's the estimated probability that a randomly selected customer downloads 3 or fewer songs? Well, notice that the way I write the probabilities here is it's the probability, and in parentheses, it's the number of songs downloaded. That's the variable we're looking at. So they're saying 3 or fewer, so that would be P1 plus P2 plus P3. They don't have any choice here of 0 songs downloaded. It starts at the 1 song downloaded or 2 or 3. And then I just looked up the probabilities that were just below them. And I just added up their respective probabilities, and I got 0.8. And then B says, what's the estimated probability the randomly selected person downloaded at most 3 songs? Well, that's the same thing as saying 3 songs or fewer. That's exactly the same answer. So what they're really testing you here is to see if you understand the language. Some students don't understand this language. Maybe they don't use it very often. When we say 3 or fewer, or at most 3, that means exactly the same thing. All right. Okay. And sometimes you hear the term no fewer than. If I said no fewer than 3, that would be 3 or more. All right. But again, many students seem not to know these things for some reason. I don't know. All right, 23 is another problem here where we're listing events. In this case, it has to do with 2 claims, medical insurance claims, where the C represents that the medical claim was covered by the insurance company and it is not covered. So these are the 4 possible events for the 2 claims. Either both claims are covered, the first claim is covered and the second isn't, the first claim is not covered, the second one is, or neither claim is covered. And then they give you the probabilities of these events. They give these to you in the problem. And then they give you events and ask you for the probabilities of these. And I'll let you look at this on your own. I think this is pretty logical to figure out. All right. For example, at event A, B, at most 1 patient is covered. Well, that would be these first 3 events, right? It would not include It says, oh, excuse me, it says at most one patient is covered. So that means either no patient is covered or one patient is covered. So it would be these three events here, O2 and O3 and O4. Obviously, O1, both claims were covered, and that would not be it. So there are three outcomes to event A, and the probability of event A would be the number of outcomes in event A divided by the total number of outcomes in the sample space, which is 4. And then B is two patients have the same coverage, right? Or same coverage. It's actually coverage type, which means they either both were covered or they both were not covered. That's what the book says. So there's only two outcomes there, and that means there's 1/2 probability. And then section 6.4 has to do with conditional probabilities. This is number 39 in 6.4. Where again, they give you a table. This is the table. Now, the table does not include the totals here. I put the totals in. So if a table does not give you totals, you need to do the totaling yourself. Not a big deal, because you have to calculate probabilities. Now, what are the two variables here? Age, there's two age groups, and then there's two statuses as far as tattoos are concerned. In other words, somebody was asking a question like, how many tattoos have you received in the last year? And so they give, different answers for that, or maybe the answer is 0. So what does the person who created this table do? They just added up all the people who answered at least one tattoo, and then they added up all the people who said no, 0 tattoos. So these are the choices here. There's 100 people in the sample. All right. So the probability, if you selected somebody at random that they had a tattoo, is simply the number of people who had tattoos, 24, divided by the number of people in the study. All right. Now this one is you have to think about this one. The probability that you have a tattoo, given that the person had an age of 18 to 29. Now, what does that mean? That means you selected somebody at random, and that person is between 18 and 29 years old. All right, so you know that. And how many people are at least 18 to 29? There's 50 of them. And how many people have tattoos in out of the 50? 18. 18 divided by 50 is 0.36. Now you could use the formula for conditional probabilities. That would have worked also. But if you think about it, this is a shortcut way of doing it. And then what's the probability that a person had a tattoo, given that they were 30 to 50? Well, that would be, how many people were at ages 30 to 50? This is a case where the person's at age 30 to 50. There's 50 of those also. That's just a coincidence here. Both of these are 50. But whatever number is in the second row here, the marginal total, is your denominator, and there's 6 of those who have a tattoo. So that's 0.12. The last one is the reverse of the first one up here, B. It's the reverse of B. They're saying, what's the probability if you select a person at random who had at least one tattoo, and that they're 18 and 29 years old? What's the probability they're 18 to 29 if you know that they had at least one tattoo? Well, how many people had tattoos? 24, and 18 of them are age 18 to 29. So it's 18 divided by 24. These conditional probabilities, you have to determine how many are in the group that we know about. Right? The age 18 to 29, there's 50 of them. The ages 30 to 50, there's 50 of them. How many had tattoos? 24. If I ask something like, what's the probability that a person aged 30 to 50, excuse me, let me say it again. What's the probability that if we know the person did not have a tattoo, what's the probability that they're aged 30 to 50? Well, if we know that they don't have a tattoo, there's 76 of those. And how many of them are ages 30 to 50? 44. 44 divided by 76 would be that conditional probability. Any questions about that? How that works? And then in section 6.5, this is one that I like because it really tests your understanding of independence, even though it has nothing to do really with statistics. But it's sort of like a little engineering problem, if you can think about it that way. Here's a system here, and this system has two parallel subsystems, you can call them. Subsystem 1, 2, and subsystem 3 and 4. Picture something like this. And it says all four of these components act or work independently of one another. So now we're going to be talking about independence, the idea of independence. All right, and we're going to be using multiplication rules. Now, the first question says the 1, 2 subsystem only works if both components work. Now, what's given here is that the probability that each of these components works, each one of these is 0.9, according to the problem. Now, it doesn't have to be that way. You can have different probabilities for each one of these. But the problem is assuming that there's a 90% chance that any one of these components, 1, 2, 3, or 4, work. And what's the probability that any of them don't work? It's 0.1, right? 10% chance of that one. So the 1, 2 subsystem only works if both components work. And what's the probability that both components work? 0.9 times 0.9. These are independent components. So we multiply their probabilities. We get 0.81. Okay. What's the probability that this 1, 2 subsystem does not work? Well, it's the complement of 0.81. It's just 1 minus that, which is 0.19. And it also asks, what's the probability that the 3, 4 subsystem does not work? Okay, does not work. Well, it's the same thing as the 1, 2 subsystem. They have the same probabilities. The answer is 0.19. That's the same. Now, C says, what's the system, the overall system doesn't work if the 1, 2 subsystem and the 3, 4 subsystem doesn't work. So both subsystems have to break down for the overall system to work, which implies that the overall system will work if at least one of these subsystems is working. That's what that means. So what's the probability that the system does not work? It's simply, well, we know the probability that the 1, 2 subsystem doesn't work is 0.19. The same thing for the 3, 4 subsystem. The product of those two, right, because these are independent, the product of those two is the probability that the overall system doesn't work. What's the probability that the overall system does work? It's the complement of 0.0361. It's 1 minus 0.0361. There's a 96.39% chance that the overall system works. So this problem basically lets you think about the idea of the product rule, the multiplication rule for independent events. That's really what this problem is all about. That's it for that. All right. And then section 6.6, I have a problem there, 6.75. And this one is one that I like to give on a test. So I'm giving you an example so that you will not go wrong. But if you don't study, you will most likely get this wrong because most students are not thinking through this logically when they see this problem. They don't do it correctly. So what this problem, now the Venn diagram is not given in the problem. I drew this. What's given in the problem is that this is a company, a cable company that offers at least 3 services, but they're only mentioning 3 of them: cable, internet, and telephone. And then what they give to you is this information here. They give to you the probabilities that if you select somebody at random that's a customer, they pick cable. Or what's the probability of internet? What's the probability of telephone? Now, they don't use the word probability. What they do is they tell you the percentage of their customers that have cable, the percentage that have internet, the percentage that have telephone. Well, you're going to convert those to decimals, and they're going to be your probabilities. They also give you this information here, the rest of this. They say the percentage of people who have cable and internet is 25%, cable and telephone, 21%, internet and telephone, 23%, and then there's 15% of the customers who have all three. All right, now before you answer any questions with this type of problem, what you need to do is you need to fill in a Venn diagram. Because if you don't do it, if you get this right, you may have very good mental visualization skills, but most likely you're going to get it wrong. So the best way of doing this is fill in a Venn diagram with three circles, three events here: cable TV, internet, and telephone. So what's the box? All the services offered by the cable company. Now, the only three they mention are cable, internet, and telephone. Don't assume that's the only services they're offering. They could be offering something else, they're just not mentioning it. But there's a way of double checking to see if there are any other services. Now, how do you do this problem? This is the easiest way of doing it. Now, there's a formula that you can use, formulas, but I think most of you will probably want to avoid formulas. So what you do is you start with the event of all three services being taken by a customer. There's 15% of the clients who do that, or the probability, if you selected a client at random, the probability that they would have all three services is 0.15. Where is that in the Venn diagram? It's right in the middle here. I'll put it right in the middle. This area in the middle here is all three of the events together. All three together at the same time. That's what you do next, the first. Then you work with the ones that have two services. Now you should do it in this order. This is the logical way of doing it. Now, cable and internet, let's look at the Venn diagram the way I drew it, are these two circles here. You see the two circles, cable and internet? Cable and internet together would be this entire intersection here between the two, whole thing. And it says 25%. Now, this is the mistake most students do. They'll put 25% right into this area right up here. No. This whole area is 25%. But this area is already 15. You see, you started off with the 15 in the middle here. So if this whole area is 25, then 25 minus 15 is 10, 0.10 goes here. I'm telling you, 80, 90% students who don't study this, they always put the 25% right here in this area here. It's not 25% there, it's 10%. Because 10 plus 15 is 25. That's the whole area between cable and internet. You do the same thing with the other paired services. Cable and telephone, 21%. But where's cable and telephone? It's these two circles. It's this area here. And this area here is 21%. So if the middle's 15, this must be 6, because 21 minus 15 is 6%, or 0.06. And then they say 23% is internet and telephone. Well, that's these two circles. And when you have both of them together, it's these two areas here. So if this whole area is 23, 23 minus 15 is 8%. It's 0.08 here. Now, what you're supposed to do in a problem like this is now you have there's 7 areas here. If you count them, there's 1, 2, 3, 4, 5, 6, 7. There's actually an 8th area, which is outside of these 3. You may want to ask the question, what is the probability that that somebody didn't have any of these 3 services? Maybe there's a 4th or 5th service that this cable company is offering. Well, how would you figure that out? You'd have to count these numbers up and see what they add up to and subtract from 1. But when you count up all these numbers, it actually adds up to 1. So that means that all the customers of this company either have one of these 3. Cable, internet, telephone. There's no other services offered by cable company. So the answer for the area out here is 0. There's no, but if I give you a problem, it's not necessarily true that all these numbers should add up to 1. It could add up to a number less than 1, and therefore the area out here would be 1 minus the sum of these numbers inside. All right, let's look at the questions that are being asked. Now, I put notation here, but the questions are being asked in words. All right, so this is number 75. All right, so this is part A. Let me see what they're asking. What's the probability that the person had cable TV only? That means they only got cable TV, didn't get internet or telephone. Well, guess what? You could answer this question immediately because you put in 0.49 in this area here. The answer is 0.49, 49%. That's the percentage. All right, this area here is cable TV only. It does not include cable and internet, does not include cable and telephone, it does not include cable or all three of them. It's just cable only. Next question. B. What's the probability that the person chose internet if they what's the probability of internet given that they have that you know that they have cable TV? In other words, what's the probability that if you know that they have cable TV, what's the probability they have internet also? Well, this is that conditional probability. If you know that they have cable, you select them at random from the cable group, what's the probability that they have internet? Well, we can use that formula that they use for conditional probability. It's the probability that cable and internet is chosen together, divided by the probability of just cable. Well, those numbers are given in the actual problem. Cable and internet together is 0.25, and cable is 0.80. The answer is 0.3125. So if it's a conditional probability, all right, and actually they do use notation here. They don't use English. They just say, what's the probability of internet given cable TV? It's better just to go ahead and use that formula, the conditional probability. C, they're asking, what's the probability that exactly 2 services are offered? That means 2 services only, right? 2 services only. Exactly 2 services. Which areas are they? It's these 3 areas, these areas right here. This area here is cable and internet only. This number here is cable and telephone only. This number here is internet and telephone only. Since they asked what's the probability exactly 2 services, you would add up those 3 numbers, 0.10, 0.06, and 0.08. The answer is 0.24. D says, what's the probability of internet and cable TV only? Well, that was just one of those 3 that we just counted, right? Internet and TV, internet and cable TV only. And obviously, it's this one right here, 0.10. That's the one that's one of the 3 that you added together in part C. Now, I added, without giving you the answer, 3 additional questions. First question is, what's the probability of having none of these services? I think I sort of gave you the answer before, but that would be the probability of having none of them would be the probability of outside of these 3 circles. It would be in the box, but outside of the 3 circles. All right, that's the probability of not having either cable or internet or telephone. Again, you take 1 and subtract the sum of all these numbers in there, and that gives you your answer. What's the probability of exactly 1 service? Well, that would be the sum of these 3 numbers, 49, 09, and 03, wouldn't it? It would be cable only, internet only, telephone only. That's the probability of it getting exactly 1 service. It's either cable only, internet only, or telephone only. Be the sum of those 3 numbers, 49, 09, 03. And finally, the last one, what's the probability of at least 2 services? Of at least 2. The answer to that question, if you think about it, would be the probability of having none of the services, plus the probability of having exactly one service. If you add those two up and subtract from one, that would be the probability of having at least two, which would mean the probability of having exactly two plus the probability of having all three. All right, so hopefully your mind is not totally twisted and tired by this time, but that's really how you do a problem like this. Remember, if you create your Venn diagram and fill in the numbers here, it will be very helpful in answering the questions. All right, if you don't do that, good chance you're going to get questions incorrect, especially the conditional probability ones. Any questions about the problems in section 6? These are the ones that, now on your next test, am I going to ask every single one of these questions? Well, first I'm going to change the problems, right? But I'll ask questions like these with different numbers and different, words and things like that. But yes, I will ask questions like these, but not all of them, because there's the next test will also have chapter 7 in it, so we're not going to be, giving so many questions from chapter 6, but I will select the ones from this list here, and then there will be homework, which will also be these problems, and in the homework I will change some of the numbers. I will maybe ask different questions, but it's basically the same problems. All right. So the homework is going to give you practice doing these with this being posted. And the test will test you on these types of questions, the ones that you're saying. So chapter 6, am I going to ask anything else out of chapter 6? Well, possibly a concept question, but as far as calculations are concerned, these are the types of problems I will ask, but maybe not all of them. But I will choose from this list of problems that you see here. And that way you won't go crazy trying to figure out what am I going to ask as far as probability questions out of chapter 6. Remember, this is not a probability course, so I don't expect you to be experts in probability, but I do expect you to be able to apply what you've read and learned in this chapter. And therefore, I'm giving you the types of questions. You just have to practice how to solve them. Okay? Any questions about that? All right, so let's start we're going to start chapter 7 today, and we'll continue on. Now, we're supposed to be completing chapter 7 next Monday, but it's possible some of it will go into next Wednesday. But don't worry, we'll eventually catch up. So I'll stop sharing this. Again, I'll post that a little bit later. It's like somebody has said something in the chat. Oh, somebody was late. That's okay. All right. So let's share the PowerPoints, and I don't see them even listed here, so I have to actually go and highlight them. Okay. Now, what is chapter 7 all about? Now, chapter 6 is an introduction to probability, just to give you give you some idea of what probability is, how to do some probability calculations, but there are certain things in chapter 6 that we're going to carry over into chapter 7. That is the idea of mutually exclusive events, the idea of independent events, the multiplication rule, the addition rule, things like that. All right. Now, chapter 6, I did leave out quite a few things, especially in section 6.6. And I think there's a 6.7, which I didn't cover at all. But there's more complicated things in 6.6 I did not cover. So please, if I did not cover it, even if it shows up in your in the PowerPoints, well, no, if it shows up in your book, in your ebook, things like Bayes' theorem and the law of total probability and things like that, if I didn't go over it, don't worry about it. All right, I'm not going to ask you any questions about those. All right, but this chapter here is really the next step in your understanding of probability, because now what we're going to do is we're going to talk about the variables that actually have values associated with them and probabilities associated with them. Okay, so you know the word variable comes from algebra. We talked about variables, we talked about x, we talked about y with variables, right? And we plotted them, and we did equations with them, right? And but now what we're going to talk about is a new type of variable called a random variable. We're going to assume that the variable's values are random. They occur randomly. All right. There's a in the book they talk about um, variables being deterministic versus random. But deterministic means the equation works all the time. All right. You know, if you think about equations in physics or chemistry, whatever the equations might be, they're exact equations. All right. But in statistics and probability, things aren't exact. Things are uncertain. So random variables have values which we're not sure will occur. But if they do occur, they occur with a certain probability of occurring. All right. So this is the formal definition of a random variable. A numerical, now it's numeric, can't be a categorical variable, whose value depends on the outcome of a chance experiment. A random variable associates a numerical value with each outcome of a chance experiment. So we'll see examples of this in a minute. A discrete random variable means that there is a limited number of these possible outcomes of a chance experiment. Right? There's a limited number of them. You can count them. All right. If you roll a die, the dice, you know that there are 6 possible outcomes. If you flip a coin, there's 2 possible outcomes. That's what we mean by discrete. You can actually count them on, and we can actually plot the number of times that they occur on a number line. A continuous random variable is one in which there are an infinite number of possible values inside an interval on a number line. So you can picture creating an interval on a number line, and any value in between that, those endpoints of the interval, could be a possible value for the random variable. So obviously, we're going to talk about the discrete case first, so you understand that first. All right, now in this case here, they say they're going to use, in this book, they're going to use lowercase letters to represent random variables, okay? Lowercase letters instead of using uppercase letters. All right. Now, it says here, a discrete random variable is usually the result of counting, the number of items purchased, the number of gas pumps in use, the number of broken eggs in a carton. All the possible. For example, if you let me let's see if I can have an example. All right, suppose we flip a coin 4 times. All right, we flip a coin 4 times. What are all the possible values of the number of heads that we could get in the 4th coin? Well, we could get 0, right? We could flip the coin 4 times and get all heads. So 0 is one answer. We could get 1 head. We could get 2 heads, or we can get 3 heads, or we can get all 4 of them being heads. That makes sense? That's an example of a discrete random variable, where the random variable takes on the values 0, 1, 2, 3, or 4, which represent the number of heads that you get in 4 flips of a coin. Okay? That's an example of a discrete random variable. Continuous random variable has to do with measuring. Something that we're measuring. All right? It could be temperature, weight, height, time, whatever it might be. We're measuring something, and now the number that is the result of the measurement could be limited into 1 or 2 decimal points just because of the limits of the measuring instrument, but it doesn't mean that it couldn't be any other number. It could be a number that goes out to 20 decimal points or 1,000,000 decimal points. So the whole point is continuous random variable has an infinite number of possible answers. All right. So here they're just giving you an example of a discrete one. An experiment. So this is an experiment in which the type of book, print or digital, chosen by each of 3 successive customers making a purchase of a single book from an online bookstore. Define a random variable X, the number of customers purchasing a digital book. Okay. So there's 2 choices, digital and print, right, for each of the 3 customers. We're really saying, what are the possible values for X, the number of customers purchasing a digital book? Well, it could be that the 3 successive customers all purchase what? Printed books. So the answer would be 0. It would be none of them purchased a digital book. So it's 0, 1, book was purchased, 2 books are purchased, or all 3 are purchased. All right? So 0, 1, 2, 3 are all the possible answers to this question, the number of customers purchasing a digital book. Because there's only 3 customers, it has to run from 0 to 3. Okay? So that's how you come up with your values for the random variable. Now, in many cases, they'll give you the ones, but you can see here are the values 0 up to 3. So the possible X value is 0, 1, 2, 3. Okay. Sometimes random variables occur in analyzing sample data chosen from a population. Right. So here's an example here. Suppose a high school counselor plans to select a random sample of 50 seniors, and they're going to ask each one of these 50 seniors whether he or she plans to attend college. All right. So they're being asked, are you planning to attend college? I guess the answer is yes or no. So this sampling is another way of looking at a chance experiment. Now, a chance experiment is repeated many, many times, right? We call those trials. We can consider that the number of observations, the number of people in the study or in the sample would be the number of trials. It means the same thing. So the sample space is what? It consists of all different possible random samples of size 50 that might result, right? And for a simple random sample, each of these outcomes is equally likely. All right. So they might be, you might want to count the number of students in the sample who plan to attend college. Well, there's 50 people in the study. So it's possible all 50 of them say, no, I'm not going to attend college. So 0 is the smallest value for this random variable. And then it goes all the way up to 50, right? It's possible that all 50 of them say yes. Does that make sense? So this random variable, the number of students in the sample who plan to attend college, could go from 0 up to 50. Now you might say, well, wait a minute, I did the sample, I know the answer. No, this is the probability before you do the sample. You're planning the sample, you're planning to ask 50 people. You haven't chosen those 50 people yet. Okay. And you want to know the probability. You want to list all the possible numbers of students who could plan to attend college. So it could be 0. In other words, all 50 of them say no, and it could run up all the way up to 50 saying yes. Any questions about that? So that's how they come up with for many of these random variables, that's how they come up with the actual values. Right? It's just logical common sense, basically. If you're asking 50 people, do you plan to attend college? You want to know what are all the possible numbers of those 50 people who say yes. Well, before you actually ask the question, it could run from 0 all the way up to 50. All right, so that's it for this section 1. We're going to do now section 2 of chapter 7. That's probably all we're going to get to today. Share that. And now we'll get to section 2, and looks like I don't see it here yet. All right, let's see. All right. All right. So we have these things called random variables. We're going to deal with the discrete random variables first. We're going to talk about what are called probability distributions. Now, just a minute ago, I gave examples where we could list all the possible values for a discrete random variable, like from 0 up to 50 in that last example. A probability distribution for a random variable would be a list of all those possible values and their respective probabilities. Each one of those possible values will have its own probability. And that's called a probability distribution. The list of all possible values and each probability that's associated for each one of those values. Okay? So, probability distribution of the discrete random variable gives the probability associated with each possible x value. Each probability is the long-run relative frequency of occurrence of the corresponding x value when a chance experiment is performed a very large number of times. In other words, if let's say we have a survey and we do the survey to 1,000 people, all right, and then we find and we ask them a question like, do you plan to attend college? And we find out of those 1,000 people that 600 of them say yes, then 0.6 or 60% would be the long run relative frequency. We can use that as an estimate for the whole population. That's the whole idea. That's really what they're saying here. Now, how do you display a probability distribution? Use a table, a histogram, or a formula. The tables are very common. How do we write these probabilities? Well, if the random variable has a value of x, if the random variable x is a value of 2, we could write it as its probability is P2. That's the way I do it. All right, P2, and it means P of x is equal to 2. What's the probability that x is equal to 2? So P5 would be, what's the probability that x is equal to 5? All right, so it's just a shorthand way of writing the probability for one of those values. Okay. All right, so this is an example here. And I guess we'll just have a chance to just do this one. Suppose that each of 4 randomly selected customers purchase a refrigerator at a large appliance store. They choose either an energy efficient model or one from a less expensive group of models that do not have energy efficient rating. Right? So it's either energy efficient or non-energy efficient. Suppose that these customers make their choices independently of one another. Notice we say independently. And that 40% of all customers select an energy efficient model. So this is the long-term relative frequency of somebody, if they're chosen at random and they're going to choose a refrigerator, they're going to choose the energy efficient one. Can somebody tell me what the relative frequency would be for the other type? For the non-energy efficient one. If 40% are choosing the energy efficient ones, then what's the probability of the G, the less expensive brands?
60%.
That's right. It's 1 minus 0.4 because that's it, right? The refrigerators are either energy efficient or they're not. That's where they come up with the 0.6. All right, so there's 4 of these customers, right? Did they say that? There were 4 randomly selected customers. And so one possible outcome would be that the first person that comes into the store chooses the energy efficient one. The second one chooses the less expensive one. The third person chooses the less expensive one, and the fourth person chooses the energy efficient one. What's the probability of this particular event that these 4 people select in this order here? Well, we're saying what's the probability that the first one chooses energy efficient, the last one does, and the other 2 don't. 2 in the middle don't. We simply multiply their probabilities because we're asking the question of what's the probability of each one of these people choosing this particular type of refrigerator. We multiply these, 0.4 for the probabilities of E, 0.6 for the probabilities of G, and we get 0.0576 or a 5.76% chance that this particular combination of 4 customers will occur. Here's another possibility. Well, it's the same, it's going to give you the same answer. It's just the order's different, right? The order's different. Now the first and the third person is choosing the energy efficient ones. You get the same answer. This one down here is a little different though. 3 of them are not choosing, the first 3 are not choosing energy efficient, but the last one is. Okay. So X is the number of energy efficient refrigerators purchased by the 4 customers. What are the possible answers? Can somebody tell me what the possible answers are? Remember, there's 4 customers, and they have the choice of energy efficient or non-energy efficient. Can somebody tell me what are the possible values of this random variable? The number of energy efficient refrigerators purchased. Assume that you don't know ahead of time who's going to choose what. What are the possible numbers of people choosing energy efficient refrigerators? Starts off at what number?
0 to 4.
0 to 4, absolutely. Either all 4 don't choose it. That would be G, right? And then 4 would be E, right? And then all the other possibilities. Two of them choose them, two don't. All those possibilities. Then 3 choosing energy efficient, and 1 did not. All those possibilities are there, and then we have to determine the probability of each of those events. Now, we already know the probabilities of what? We know the probability, where is it? Well, we didn't do it yet. What's the probability that all 4 choose energy efficient? It would be 0.4 times 0.4 times 0.4 times 0.4. It would be 0.4 to the 4th power. That would give you the probability that all of them chose E, right? All of them chose energy efficient. You could also calculate the probability that all of them did not choose energy efficient, which would be 0.6 times 0.6 times 0.6 times 0.6. So we could figure out those probabilities, but the question is, how do we figure out all the rest of them? All right, we'd have to list them and figure them out, basically. And when we did that, and this is one way of doing it, we'd actually list all the possible outcomes. Okay, how many outcomes are there? There's 16 of them. And we would have to figure out each of the individual probabilities, and then we list the X values. X is the, for example, G, there's none energy efficient. E, G is 1, and there's 1 here. And then, you know, you go down the list, you just count the number of these. 4. And then for each value of X, you add up the probabilities. For example, 0 and 4 have only 1 probability. But how about 1? There are 3, 1. See, there's 4 that are listed here that have an X value of 1. So you have to add up these 4 probabilities, get the probability that X is equal to 1. There's 1, 2, 3, 4, 5, 6 that are equal to 2. You have to add up those 6 probabilities, get the probability that X is equal to 2. Same thing for 3. Get the idea? And then you end up with, hopefully they have it listed here, a table. Then, yeah, here they are, right here. This is called a probability distribution. You're listing all possible values of X, and you're listing their respective probabilities. I'm running a little bit over. I apologize for that. Any questions about this? Because this is a very important concept. We're going to continue with this on Monday. Now, before you go, I'm going to make a note where I'm stopped. Here it's number 6 and number 12. All right. And so what's going to happen before Monday is, number 1, I will create that quiz and post it. It will probably be done by Friday, but again, you'll have access to that PDF that I created that I went over today, and it'll be a guide to do the homework. So it'll be available on Friday, and then you'll have until Monday to complete it, Monday before class. And then on Monday, in addition to what I'll be teaching, there will be a vocabulary quiz, concept quiz of dealing with chapter 6. All right. So there's be another quiz, but it's both basically vocabulary, should be very easy. This is not, I mean, there are obviously plenty to choose from for vocabulary, but it should be pretty easy because I'll be taking it right out of the book. All right, so there'll be another quiz for chapter 6. Any questions? That's it. All right, so that's it for today. I'll stop the recording.